Today I'm going to be talking about some work that I have been doing in collaboration with Sean Kahn from the UN Environment Program, Brian Sullivan here at Google, and then Randall Martin, formerly of Dalhousie University, now at Washington University in St. Louis. And the goal of this work is really to help the UN set up a global air quality monitoring framework. If you take a look at Africa and some other regions of the world as well, you can see that there's very sparse surface measurements. I'm probably missing some, and I think we have colleagues in the room here who will probably speak to additional measurements. But in Africa in particular, the number of air quality measurements that we have available really is very sparse. And if you compare that to what we're able to see with satellite observations, you get much better coverage with those satellites. And so the goal of this program is to both provide a platform where surface measurements can be collected, organized, quality assured, and in general prepared to be used to understand air quality in the location that they're collected, but then to also be able to merge that with satellite observations to fill the gap in air quality information and provide surface measurements in locations where we currently don't have observations from the ground. And I'll be primarily talking about the satellite observation portion of this in my talk today. So we, as part of this work, are setting up an international data fusion system with the goal of providing near real-time, high spatial, and high temporal resolution data for surface level PM 2.5. And the map you see on the right here was actually generated using the data that we're pulling into Google Earth Engine to calculate surface level PM 2.5 using satellite observations and model data. The system offers a couple of advantages. One is that we get some coverage, so it's a first cut look at what's happening on the ground with air quality. We're able to get the high spatial resolution using some new satellite data products. It is available in near real time, so we're able to update this much more quickly than some of the much more validated and well-established products that you see that maybe take a couple of years to produce, and we're also able then to pull in data using regulatory grade monitors and with the potential to incorporate low-cost monitors as well. So we use a few data sets in this work. I won't belabor what we have here, but essentially what we needed to use to be able to produce these data sets are aerosol optical depth retrievals, and I'll talk a little bit more about those in a second, from MODIS, along with model data from the European Copernicus Atmosphere Monitoring Service, model data, and then ground measurements of PM 2.5, along with a PM 2.5 data set from Dalhousie University, or formerly Dalhousie University. And we incorporated those data sets to produce this fused product using the processing shown here. So we take the satellite images, which give you aerosol optical depth. It's a measurement of total column aerosols all the way from the surface up to the top of the atmosphere. We use that data then to, in combination with model output from CAMs, to estimate the surface level PM 2.5 at high spatial resolution using the MIAC data. And then we combine that using interpolated surface level data to get a fused PM 2.5 data product. And so I'll talk a little bit at the end about the fused product, but primarily what I'm going to be showing here in a moment are the MIAC surface PM 2.5, mostly without the surface measurements. So a little bit about the theory of what we're doing here. You can imagine a satellite up in space looking down at the surface of the Earth. And what it's seeing is the total aerosols, the smoke close to the ground, smoke that may be aloft from wildfires. It's seeing all of that and creating a single measurement of what's in the atmosphere between the surface of the Earth and the satellite. And so the main question that you have when you have that data point is, where in the vertical column is it? Is that pollution at the surface where people are breathing it and their health is being impacted by that pollution? Or is it aloft where it's maybe important for atmospheric chemistry, but not directly impacting health? And so the role of the modeling data in all of this is to help us translate that number of aerosol optical depth down to a surface level PM 2.5 estimate. And so the CAMS photochemical model breaks the atmosphere up into boxes like this, where you have air parcels aloft, and then also air at the surface. And so the vertical layers get summed to produce an equivalent of the AOD calculation that you get from the satellites, and then that's compared. And then you also have the lowest layer, which gives you the ground level PM 2.5. And using that relationship, we're able to convert the satellite AOD down into surface level PM 2.5. And that's what we've been able to do with Google Earth Engine at scale really quite easily. So what I'm showing here is a year's worth of weekly average data from that process that I showed a moment ago, where we are able to, so this covers 2018, January through December on a weekly basis. And you are able to start seeing broad patterns in surface level air quality from this data. So just as an example, if you watch the Central Africa, there's some fires cropping up right there, moving southward over time. You're also able to see some seasonal variation in the pollution around Johannesburg in South Africa. And then Saharan dust also lights up there in northern Africa, where you're seeing at particular parts of the year really quite intense surface level PM 2.5 coming from this product. We're also able to look directly at the daily level data, and so we have that available for 2014 through early 2019 at the moment. And what you can see here is just an animation of being able to dig into the data. We're able to go through, look at each day. This was a hotspot that showed up, and okay, it looks like there's a plume there, and if you go into the visual imagery, you can see indeed there was a fire burning in that location at that time, and the smoke really shows up there. So this is a really exciting product. It's a first cut, and I think the question is, how well does it do? This is a question that we are working on answering. Given the sparse measurements that we have in Africa, we've started doing a validation, and what we see from the satellite-only product is that in some locations we're really not doing well at all. The surface level data don't agree very well, and in other locations we'll see much higher correlations in the range of 0.5, 0.6 R squared. So that's R squared, not correlation. But it's doing well as a first cut, and to our knowledge, this is the first product that has the potential to be available in near real time at a 1 kilometer spatial resolution in this region. So we're excited to have this available and to begin to produce it on a regular basis so that we can continue to evaluate and do a better, improve upon it, do things like gap filling potentially here, and we've got some interesting approaches that we might be able to use there. And then also, doing some bias correction. You might be able to compare this to surface observations of aerosol optical depth to improve the relationship. So there's a lot of cool ideas. The last thing that I'll touch on is we also have tried fusing in the surface level data and producing a fused product using both the satellite observations and the monitors. Unfortunately, there's very few locations where you have monitors close enough that you could validate between the two. But we did have 2 sites where we were able to do that, in Addis Ababa and then on the right in Senegal. And what we see is that depending on the location, the proximity of those monitors and how well the satellite product is doing in a particular location, we're able to get fairly good agreement between a validation site and a fused site. So this is an exciting direction as well. And as available surface level measurements expand, as we see the monitoring network on the ground expanding, there's going to be an increasing number of locations where we can start to do this type of fusion. So just to summarize, this is a work in progress. We're pushing toward really putting this into a framework. Sean is leading the charge there, and I think that's pretty exciting. Some of the benefits of what we're trying to do here is that we think it really helps to fill the gap. It's giving us near real-time information where we don't have much at the moment. And it can be potentially useful in a number of different applications where folks might, for example, want to think about using this product to think about where they're going to site a monitoring campaign, or to help understand what's happening in near real time when an air quality event occurs. So a wildfire near a large population center or other sorts of events where understanding what's going on with air quality is potentially valuable. So where we have them available, fusing in the ground level observations is going to be really beneficial, and we hope to be able to use new data sets. So love to talk with anyone who has thoughts there. And then we're moving toward producing this in an operational near real-time basis. And using Google Earth Engine, it's actually quite easy to do that globally rather than just for Africa. So the goal would be to do it there. And if we have Asia or North America covered, then it's going to be a lot. We're going to have a whole new realm of validation available to us. So that's all. That's me. And thanks so much.
You're making progress. Awesome. Okay, do we have we can take one question or two short questions. Rima. Yay.
Hi, let me start us off.
Can you use a microphone? Because since we're recording. Thank you.
Great job. Very nice talk. So can you tell us a little bit about your thoughts on what's driving all that missingness in the middle? Is it more like clouds?
That's cloud cover. Definitely
Okay.
cloud cover. Yeah,
Thanks.
it's very cloudy in like Central Africa and on the southern coast of West Africa. So yeah. One of the downsides of satellite data.
Yeah, sure.
Are you working with anybody on the ground as far as giving them this data? You were talking about potential sighting advice that you could take from this.
Yeah, definitely. So Sean's leading the charge there, as I said. But I think there's interest in understanding whether this can be helpful for some work in Addis Ababa and several other cities that they're talking to. So I don't know that anyone. Yeah, I think there's discussions going on about how those could be used in various places. So definitely, I'm not the one necessarily having those interactions, but they're certainly happening.
Our next speaker is Scott Weichenthal from McGill University. He's going to come talk about deep learning for air quality. Please join me in welcoming Scott.
Hello, everyone, and thank you to Karen for letting me know about this amazing meeting that we've all been at. So I'm going to talk a little bit about a project we've been doing over the past year to try and extract exposure information from pictures. So I'm an epidemiologist and exposure scientist, and in order to do a health study, you need to assign people exposures. And the way we normally do that is either through physically based models where you have emissions data, you model those emissions and their distribution through the environment, and then you assign an exposure based on what you know about how that emission is transported. The other method are geostatistical models, often called land use regression models, where basically we blanket an area with monitors, we extract land use information around all those monitors, and then we develop some kind of linear regression model to predict exposure where we don't have measurements. So there's a number of limitations to these factors. Often the geographic predictors are limited in scale. So this is Toronto. Millions of people live outside that shaded area, but we can't get an exposure for them because the GIS data doesn't exist the minute you step one step outside the official city boundaries of Toronto. Okay, so that's a big limitation of how you can actually estimate exposures for people when you're thinking about a large study. Also, generally these models predict one pollutant at a time. It makes it difficult to evaluate interactions between various aspects of the built environments and how they may impact exposures. And GIS data doesn't really reflect the world how we experience it. And so that got me thinking about images, right? So I've spent a lot of my adult life measuring air pollution exposures, and a lot of the things that influence our exposures are captured in pictures. So a busy street obviously has a lot of environmental exposures we know about, but it looks a lot different than a residential area or a park. And this is true at a local level, but also at a satellite level, right? So an industrial area looks different than an area with a lot of farming or a small town. And so there is exposure information in these images. And our hope in this project was to see how can we actually tease some of this information out. So how did we do that? So first, we had to find a big database. So we used the WHO database of about 6,000 locations with ground level PM 2.5 measurements over multiple years. So it's about 20,000 images, primarily between 2010 and 2016. So we downloaded satellite images from the Google Statics API, Static Maps API for each of these locations, and then we trained deep convolutional neural networks to predict the ground level PM2.5 directly from the images. So just in case people don't know what deep convolutional neural networks are, I didn't know up until about a year ago. So essentially what the goal is here is to take information reflected in an image and basically through the network represent it as in a different way. So an image is a series of pixels, and what generally gets learned, oh, what'd I do?
That's good. There's no laser pointer.
Oh, there's no laser
Sorry,
pointer.
sorry.
So an image is a series of pixels, and basically what gets learned in the network you can think of as weights. So you learn these weights to convert information in a picture into information in a concentration. And so how does this happen? So basically you feed the image into the network, the image runs through the network, you get a prediction, and then the network compares that prediction to the true known value, gets it wrong, and then it says, well, let me update all the weights in my model so that I do a little bit better on this example. And then it runs again. And it basically just does that over and over again until you reach some minimum loss function where you're sort of as close as you can get to the true value based on the information you've put in. So what do we find? So this is our results for global PM2.5, the annual average PM2.5, the measured values on the y-axis and the predicted values on the x. And this is just with the picture. We can explain about 75% of the variation in ground level PM2.5, which blew me away when we first did this, because I thought, well, maybe we'll see something, but this was much better than I expected we would see. The other advantage of these networks is that you can actually sort of visualize what's being used in the images. So these are called gradient-weighted class activation maps. And so we can't tell exactly the ground level features that are being used, but you can see that on the diagonal, the sort of local level things that are being used. Okay, and when we look more closely at what the filters are representing, the model's learning colors, so like green spaces, blue spaces, road type colors like grays, and also geometries, so grid type patterns, and then complex combinations of colors and patterns. So that does make sense intuitively with what we know about air pollution. So how do we compare to the best in the world? So the sort of best model now for estimating ground level PM2.5 is the global burden of disease model. And on average, there are 12 micrograms per cubic meter square off the true value. So we're not quite as good, but we're surprisingly close because there's a lot of complicated things that go into the GBD model. Aerosol optical depth, chemical transport models, ground level population data. Our input is just a picture. And we did a direct comparison, so the nice folks at GBD actually said, why don't you compare your model to our model? And when we do that, we see that basically there's a very strong relationship between our predictions and their predictions, and the slope is basically 1. And we're still getting better. So this is the latest result from August. We found that when we combine 2 images, sort of a zoomed out image and a zoomed in image, you do a bit better. So you're capturing sort of more local information on the built environment and then sort of more regional information on the built environment. And that does a little bit better. So there is a disadvantage in that we don't have a temporal component yet, right? So if the picture doesn't change, we can't change our estimate. And so we're working to incorporate sort of time varying factors in our model that will allow us to scale our estimates either forward in time or backwards in time. So with that, I think I just want to summarize that it does seem that we can use these models to extract exposure information from images. And you can think of them almost like a traditional land use regression model, but you haven't specified what the predictors are. You're kind of letting the model figure out what the predictors are. The downside being you don't know what the predictors are. But you can learn something by using the visualizations that I've shown. Ultimately, I think this will be useful for providing a sort of best guess in places without ground monitoring data, or as you can think of using this possibly as a prior, so a prior information in a more complicated model. So you can start by saying this is our best guess based on what the place looks like, and then you can complement that with all the other data sources that might be available to you to try and improve the model. We're also working right now to try and incorporate temporal information into this, and we're working to collect street level information. So we have students going all around Montreal and in India also collecting images with GoPro cameras, with air pollution monitoring backpacks and noise, and trying to do this at a more local level. This is published in a paper from the ICML conference this year if you want to read more about it. With that, I just want to say thank you and thank Chris, who did most of the modeling for this. He's in the room. So thank you very much.
Awesome. he finished early, so we have time for questions. Does anybody have any questions? Yes, Ollie, you have a question. There are microphones in the back. Can somebody hand him one of those?
Hello. Yeah. This is very cool. What is the highest resolution satellite data that you were looking at, or was it like aerial data, or
It's the-
was it really satellite data?
So the actual product we're using, it's
Yeah, like the GG map.
we use the
Tiles.
R package GG map.
Mhm.
So it's from the
But
The
what
Google-
zoom? I guess what zoom?
oh,
level?
what zoom level? It
Yeah.
was 13. A 13 and 16 I think was the best model. Yeah. So we started with just one image, and then we tried models with two images, and I think it was the combination 13 and 16
Gotcha.
that did the best. Yeah.
Okay, because we do like, I'm a Google person, so we do manipulate those pixels to make them look pretty, so they're not exactly like, it's not like Earth Engine, right? It's not a real accurate measurement of the real world. So it's interesting that you're getting such a strong signal out of like objects rather than
Yeah, when we first did this, I did it as categorical because I was like, "There's no way this is going to work." So let's just see if we can do it on a very coarse, and then it just worked. I should have mentioned we're also using now using our PM model with transfer learning to try and predict components. So we have access to basically I think all existing ground level metals measurements in PM, and it doesn't do this well, but we are able to grasp some sort of components information also.
That's cool.
That's great. That's really interesting work. And I just wonder whether you thought the way of getting more accuracy is by, getting more information about the area, or actually getting more accurate and more granular PM2.5 measurements. Do you see what I'm saying? Because at the moment, if you're taking it from like WHO data,
annual average, yeah.
annual averages,
Yeah.
yeah. But when you start introducing the time, I guess you need more sensitive sensors. It might.
Yeah.
I guess the question is, what is it? Is there benefit in focusing more on that source data as well as researching the areas?
I think in order to incorporate the time aspect, we have to incorporate other things that vary in time. So we don't right now. It's not easy to get that resolution image for specific dates and times that you want. And so I think that you can think of doing a second model where you just do a regular statistical model where you have your measured value, and you have as a covariate. This is the prediction from the image, and then you can sort of add on other predictors in that model. So the deep learning model just becomes a covariate basically in your model. You could think of it if you had high resolution images for different years, then you could think about mapping it up, and then you could just scale it with the image as it changes. But right now, it's not easy to get those. Yeah, I mean, sure, companies have it, but I don't have the money to buy it.
Yeah, sure, yeah.
Awesome. Dave, is it a short one? I want to make sure we keep moving so we can get it done. Yeah, yeah.
Super short. Have you thought about like temperature or precipitation as potential covariates, or is there any limitations to that? Because that varies in time. It's cheap. You don't have to pay for it.
Yeah, it's one of those things we could look at, or you could think about surface temperature as well.
Yeah.
So that might capture something about industrial areas that isn't captured by the other built environment. So all these things are things that we're going to have to look at when we think about putting the temporal component in.
Thank you.
I know there are more questions, but hopefully we can save them for the demo pod and the pre-dinner cocktail hour. So thank you very much, Scott. Okay, so the next presentation is Sarav Arunachalam from UNC Chapel Hill. He's going to talk about also air quality predictions from traffic-related emissions. Oh, go ahead. You want to use this one? Or you want to-
I like to.
Okay, perfect.
Thank you, Karen, for the invitation and putting together this amazing panel. Who knew that Google would have a session on air quality? Fantastic. Kudos to you and your team. Thank you. What I'm going to talk about in the next 10 minutes or so is a new system we've been developing at UNC for real-time air quality predictions for traffic-related emissions. How many of you use Waze? About 50%. Okay. Now you'll see how Waze is contributing to science. Okay. Okay. So motivation, there's extensive growth of traffic emissions, both within the US and outside the US. And associated with increase in traffic emissions is the increase in exposures to these emissions. And community groups across the world are very interested in being active in local scale initiatives that seek to mitigate these harmful conditions. And in general, the lack of tools for planners at the local scale to look at what kind of tools may be available to look at possible options for mitigation. And more recently, you may have seen initiatives about transportation planning, specifically looking at things like congestion pricing, i.e. New York City, or creation of fossil-free zones, i.e. London, for example. So there's a lot of interest in looking at community scale tools. So we started thinking about how to perhaps come up with some kind of a tool which could lead to some contributions in this direction. So why near road emissions? On the left is a map which shows the number of people or the percent of people who live close to roads. This was published a few years ago. We have 1 in every 5 people in the US live next to a highway. Highway is defined as a road with a lot of traffic activity. Of course, there are traffic emissions associated with that. And if you're in some of the large populated areas like Southern California, this may be even more than 50% of the people in a county living next to a major highway. Then why is that important? If you look at the right-hand slide, you have a synthesis study that came out about 9 years ago, which shows the effect, or rather the drop-off of traffic-related pollution at very, very local scales. Okay, so what you have is if you normalize to 1 on the y-axis, you see within the first 100 to 200 meters, the traffic-related pollution having a rapid drop-off. So it's the first 100 to 200 meters that you're really interested in. We see how from a scale of 1.0 on the y-axis, you come down to nearly background concentrations within the first few hundred meters. So you want to capture this very, very local impact within the first 100 to 200 meters next to a highway. Okay. Then when I think about this, I also want to think about spatial scales. So early on, you saw some of the earlier speakers, specifically Nathan, I think, talked about grid scale models. And when you use grid scale models, either at regional to local scales or global scales, you discretize the space into uniform grid squares, depending on the type of model you use. And in these grid squares, here is one example I have. So this is California. And since there's no point, I'm going to try not to hit this again. You have the San Francisco Bay here, and that's Oakland out there. And if you're resolving this region of California into 36 kilometer squares, you see this top left figure, which shows this uniform pattern in this grid square, this entire cyan color you have. And then if you resolve into 12 kilometer grid squares in the bottom left, you have this again, very uniform green color showing there. And then if you look at Oakland, that's the figure on the extreme right there. So within Oakland, for example, any urban area, for example, you have highways and a lot of local roads and so on. And then the pollution due to these local roads or highways vary a lot. If you look at the scale on the extreme right figure, you see the extreme variability that you have. Sometimes there could be order of 10, for example, between the lowest and the highest concentrations. But you look at grid-based models on the left panel, they are dividing them uniformly, and then you have very homogeneous concentrations, and you lack the spatial texture that goes with capturing the particular texture that you have on the right-hand side. So that's exactly the kind of tool we want to look at. And depending on the study you look at, we did a study sometime back, one of my former students, which showed that using grid scale models like you have on the left-hand side, you could be under-predicting PM2.5 based health risk by up to 27%. We did this pilot in central North Carolina. We're trying to scale that for the rest of the country for now. So the point is, you have spatial homogeneity on the left-hand side, but then you want to capture the very sharp gradients next to a highway, as shown on the right-hand side. So what we did the last few years, our group has been developing a series of models, starting with this R line, which is a line source dispersion model. This came out a few years ago for representing traffic-related pollution as line segments along highways. This was applied for a large epidemiology study in Detroit a few years ago called the Nexus, and a few papers came out. And since then, we have been enhancing this particular model to look at dispersion and basic chemistry for some of the chemical processes, say, for example, dispersing NOx and then converting to NO2 chemistry to look at some of the issues like you pointed out for ozone example. Okay. Then we took this model and then developed a series of web-based models, going back to my first motivation, which is communities are interested in using rather reduced form models which are easy to use, and came this family of tools called C tools. And last year, thanks to Karen, I gave a demo of one of these tools at a demo booth outside at the similar event, and now you'll hear a little more about the same tool to larger group. So one of the members of C tools is C-Line, which is what I'll spend the next few minutes on. C-Line is the community scale line source model. It computes dispersion of primary mobile source pollutants for select conditions. It's a web-based platform. It's just like using a web browser. If you use Google Maps, you know how to use C-line. Okay, as simple as that. We combine emissions, we estimate emissions as a function of two inputs. One is traffic activity, which comes from this AADT from the US DOT, or annual average daily traffic. We combine that with emissions factors from the EPA's MOVES model. So number of vehicles times emissions factors gives you emissions. And then the users can modify the emissions for each road link by changing the traffic composition, speed, or volume. So the idea was to give the ability for users to change things rather quickly and see what if you do this, what happens. The geographic coverage of this tool is continental US, so you can go to this web-based browser and run dispersion for near road traffic pollution to get maps like what I showed earlier for anywhere within the US right now. And again, it uses the widely used Google Maps. That's the Google connection here to start with. So here's an example. This study came out a couple of years ago, a very nice study where they mapped the city of Oakland using Google Street View cars instrumented with sensors. And that's the figure from the paper a couple of years ago on the top right. Then the other three figures show the similar outputs from the C-line model, which shows a very similar layout, the part of Oakland, California. And you see these three figures. And what we did there is just to show what will happen if the ambient meteorology were to change. So dispersion is a function of ambient meteorology along with emissions. So what I have here is to show how the ambient met condition may change from the atmosphere being fairly neutral, top left, to convective, to stable. So if you have a very stable atmosphere, which is very low or nil winds, you have the highest pollution next to a highway, whereas convective is where there's too much convection activity, and so the pollution is pushed away from the highways. That's the bottom left there. So C-line helps you to do rapid assessment of what-if scenarios due to changes in any inputs, such as emissions or activity or meteorology, and that's the kind of figures you may get. Okay, moving beyond this, in the last year or year and a half, we started thinking about how to take this to the next level to do something near real time. Okay? So we took the C-line framework that you saw earlier, which uses typical meteorology and typical activity, and then did three major upgrades. The first one is moved to a more open source road network called the OpenStreetMap. And the second was to look at real-time meteorology. So earlier using met fields from the local National Weather Service station, but then we said maybe we should be looking at a product which gives you a scalability across anywhere in the US for now. And more importantly, not only look at real time, also look at some predictive ability for the future. That is, what will happen for the next few hours. So this is similar to the weather forecast model, where you may have a weather model to look at hurricanes coming, storms coming, and so on, and see what time where the hurricanes are coming. Same way, we use this model to see how the weather may be changing for the next few hours, and based upon that, modulate, change the emissions, and so on. The third input is the Google's Waze, where we were able to tap into Waze traffic data and have real-time traffic adjustment based upon what Waze was telling us. I'll talk a little bit more about this in the next slide. So with this three set of upgrades, what we have is on-demand prediction of traffic-related air pollution in 4 areas of the country. It's a pilot for now, where we set this up for Kansas City first. You may ask, why Kansas, of all the places in the US? Because EPA was conducting a field study there to look at another source problem there from rail yards. So we thought, as part of the measurements that are coming from Kansas City rail yard study, we could be doing this for near road traffic pollution as well. Houston, New York City, one of the largest cities in the world. New York City, I like New York as an area to study. And Oakland, of course, to compare with the Oakland study that I mentioned earlier, again, to predict traffic-related pollution at very hyper-local scales. And here, we were doing this, or we are doing this right now, to run the model for every hour or 15-minute frequency, but we can define every 2 minutes because Waze gives data every 2 minutes. That's the frequency at which you're able to adjust the emissions. So the road network comes from the DOT's HPMS network for 2016, emission factors from the EPA's MOVES, where you have emissions as a function of 12 road types, 12 vehicle classes, 16 speed bands, temperature. So you have this entire massive lookup table. That's the baseline. And once you have estimation of emissions from this baseline, we adjust the emissions based upon what Waze is telling as a function of traffic congestion. Start with HPMS-based traffic activity, and then for each of the 4 urban areas, we do an automated download of Waze data and AHRRR data, which is the grid-based data. I heard earlier today that Google has AHRRR coming into the Google Cloud platform, which is awesome. So soon we'll be starting to perhaps move some of our computing into Google Cloud and then maybe use her from there. But it did hear some issues about that data set, and we can talk about it later. Okay, pre-process each of the 4 urban areas, and then adjust the traffic based on Waze incidents, run dispersion, create map, push to the web server. That's the basic protocol for what we have. And we are currently running this for both NOx and black carbon, or EC25. So how does Waze affect NOx prediction? So this may be very interesting. So what I have here is, this is Kansas City, Kansas. And what you have is 2 different fields plotted here. if you look at the speed change, which is the color scheme that goes from grayish to red, right around there where I have my arrow, you have speed going down from whatever the baseline was to 55 miles per hour reduction. So that was the amount of reduction that Waze said was happening based upon us using our Waze apps at that particular intersection. And then based upon dispersion and converting from the emissions factors, you see that NOx goes up by between 40 to 88 parts per billion. So a 50 miles per hour reduction in speed led to a 50 ppb increase in NOx at that particular location. So that was the amount of information we were able to capture thanks to Waze traffic congestion. Serial snapshot of Oakland is just a high-resolution figure showing what we were able to do for Oakland. And I was putting the slide together about 2 nights ago. I think if you look at this bottom here, this is similar to looking at a radar map. If you use phone or web service, look at a radar map, you can click and see every hour what's happening. So the bottom 4 of the 4 time steps shows what happens at 12 midnight, 1 a.m., 2 a.m., and 3 a.m., and so on. And you can click on each of those buttons there to see how the air pollution fields changed as a function of what Waze was telling us. And you can see this very nice gradient you're capturing at the neighborhood scales from Oakland. Okay, the next part is evaluations. Of course, this is a study I mentioned earlier. Google did this in Oakland, and more cities are coming online. They finished one in Houston, I believe, and then the data is going to come out, and the third campaign happening in London, and there may be more. And next steps. Okay, I'm wrapping up, Karen. So the next step is we are predicting only NOx and BC as simple primary dispersion. We're going to add the conversion to NO2 based upon a work we did a couple of years ago, and then bring in contributions from other sources as background, because we're focusing more on the very, very local scales next to a highway. Connect the additional data set. This is something we can talk about later to see what we're trying to do there. But the second last bit I want to talk about is this linkage to exposure models for individuals. So based upon this live information coming from Waze and traffic pollution, we linked to an exposure model for individuals. And we just published, this paper just came out yesterday, to compute personal exposures using a smartphone app, where you bring in ambient pollution, ambient meteorology, and using that you look at personal characteristics of an individual and specific building characteristics, what may be happening in a specific building or home you may be in, and see how much of the outdoor air infiltrates into indoor and how much dose you get. And the last one is to expand to additional cities, both within and outside the US. Here's a screenshot from the Track My Air smartphone app, where you fire up the app and get ambient meteorology from the local National Weather Service station, get ambient air pollution from either C-Real or a local air quality monitor, and then you compute dose for a specific individual for the past 24 hours. So this paper just got published yesterday, like I said. With that, I have to thank my entire team and US EPA for sponsorship, and Google and Waze for giving me access to the Google Waze data, and NOAA for HRRR.